then let's just start 7.4 arc length and the surfaces of revolution. Okay, so this will be the last section for this chapter, chapter 7. In 7.2 and 7.3, we talk about the volumes. 7.2 is the disk method to find the solid from rotation of a plane region. And then 7.3 is the shell method to find the volume. So we talk about the volume in those two sections, and we also talk about the washer method. That's just basically the same as the disk method. All right. So in this section, we're going to talk about the different things, arc length and the surface revolution. So we're going to talk about the length and the area, surface area. All right. Okay, so let's talk about arc length first. So consider a curve for any curve, like in the problem in the graph. So we got something like a parabola, and we want to find the length of the arc or the piece of the curve from x equal to a to x equal to b. So let's just assume s to be the length of curve from a to b, right, as shown in the graph. So what we do is we usually, always do it the same way. We just cut this whole length into many pieces. So like the graph on the right. So we cut many pieces, and then we just consider any of those pieces and approximate the arc on that piece by a straight line or line segment. If you look at the piece, the second piece, for example, on the graph on the right, we approximate the curve on that piece by a straight line. You can see the graph, and then you can use the formula for the distance from x1, y1 to x2, y2, and this can be applied to all of those pieces. So then you just add the length or the distance of those line segments to get an approximation for the whole arc length. So again, we can write as approximately equal to the sum of the line segments. So for square root of xi minus 1 square plus yi minus 1 square. So these are the two adjacent points on the curve when we divide them or cut them. Xi, xi minus 1, yi minus 1. Those are two adjacent points like x1, y1, x2, y2. So we just use the distance formula to calculate distance between those 2 points, and then you sum up. So I will start from 1 to n. So that's the summation, the sigma notation, and then we can use delta xi to denote xi minus 1, and delta yi, the difference of yi and yi minus 1. So these are the increment in x, y direction between two adjacent points. So we can do a little change of the formula. Rewrite the expression as delta xi squared plus delta yi squared over delta xi squared times delta xi squared. In the second term, you can see you divide the delta x squared and multiply the delta xi squared. So you will not change the expression. Why do we want to do that? Then we can factor out delta xi squared inside the radical, and then when you take the square root of that xi squared, you get that xi outside of the radical. And the inside is just 1 plus delta y over delta xi squared. So remember when you factor the delta xi squared from delta xi squared, you get a 1. All right, but then that's the approximation for the organic when you add them up, all the nonsense. So in order to get the precise value of the organic thing, we need to take the limit, just like before. So we take the limit with all those delta xi's approaching 0. So you see the double vertical lines and the delta inside approaching 0. That essentially means all of the delta xi approaching 0. We are trying to cut the whole curve into infinitely pieces, and each piece is extremely short. All right. So now, so if you still remember the definition of derivative, okay, so it's the limit of the difference quotient or slope of tangent line. So delta y over delta xi is the slope of two adjacent points. The secant line, this slope of the secant line. But when you take the limit with delta xi approaching 0, that becomes the tangent line. So this quotient just becomes the slope of the tangent line, which is precisely the definition of the derivative of the function. So at the end, we got formula equal to the integral from a to b of square root of 1 plus the derivative of f squared. All right. Remember when you take the limit of this sum at the bottom line, the sum becomes the integral. So this is always the same process we do. So this is the formula. So when you actually have a problem to do, you don't have to worry about the cutting anything. Just use this formula and the problem to integrate. So let's do one example. We want to find the coordinate of the curve fx equal to x to the 3 halves from x equal to 0 to x equal to 1. So remember, you need to take the derivative in formula. It's the derivative square, all right? It's not the f square, it's f prime square. So if you take the derivative of x to the 3 halves, you get 3 halves times x to the half using the power rule. And then plug into the formula, square root of 1 plus 3 halves times x to the half square. And then that becomes 1 plus 9 over 4x, all right? Okay, so then you have to use the substitution to integrate. So we're going to let u equal to 1 plus 9 over 4x, okay? The part in the radical, we're going to denote it as a new variable, u. So, okay, so let us rewrite the result on the first line from the last page. So let u equal to 1 plus 9 over 4 times x at the part in the radical, and then do the steps of the substitution. You do the differential, you get du equals 9 over 4 dx. If you take a derivative, you get 9 over 4, but then you need to multiply dx to get differential. And then you divide by 9 over 4, you get a dx equal to 4 over 9 du, all right? But that's not the end. You still need to change the lower and upper limits of integration for this integral from x to u, because you are changing the variable from x to u. So the lower and upper limits of integration will change. So when x equal to 0, you plug in 0 for x in the u. You get 1 plus 9 over 4 times 0. So you get 1. When x equal to 1, you get u equals plus 9 over 4 times 1. You get 13 over 4 if you do the fraction addition. So now we can carry out the integral real quick. So so the integral of square root of 1 plus I over 4x from 0 to 1 becomes the new integral integral over u from 1 to 13 over 4. And the square root of 1 plus I over 4 is just squared u because u is the part inside the radical. And then dx is just 4 over 9 du as we already did on the second line on this page. So then you can integrate it easily. Take out the 4 over 9 from inside. That's a constant. So we just need to integrate the u to the half. You just use the power rule for integration. You got 2/3 u to 3/2. And then, you know, plug in 13 over 4 and 1. So 4 over 9 times 2/3, so you get 8 over 27. Remember, you multiply top by top and the bottom by bottom. So plug in 13 over 4 and 1 and subtract, you get the 8 over 27 was 13 over 4 to the 3/2 minus 1 to 3/2. Okay, so 1 to the any power is just 1. But for the 13 over 4 to 3/2, we can do a little simplification by taking the 3/2 of 4, the denominator. Well, remember, when you do the 4 to the 3/2, you basically take the root of 4 and then cube it. That's what it means by 3/2 power. So the square root of 4 is 2. 2 cubed is 8. So in the denominator, you get 8 in this first term. So it's 13 to the 3/2 over 8. And then you distribute the 8 over 27 into this two terms inside the parentheses. At the end, you get the 13 to 3/2 minus 8 over 27 if you simplify it. Okay. All right, so that's the first example. Let's do one more. Okay. Find the arclength of the curve fx equal to x cubed over 6 plus 1 over 2x from x equal to half to x equal to 2. Okay. Just do it in the same way, but this time, since we're going to use the f prime in the formula, so we need to take the derivative. So we're going to rewrite the function f to be x cubed over 6 plus half x to the negative 1. Remember, in the second term, x in the denominator. So that means the power is negative 1. Then you use the power rule for each term. You got the 3x squared over 6 plus half times negative 2. All right. So and simplify it, you get 1/2 x squared minus 1/2 x to the negative 2. And you can take out 1/2 from both terms. You get the x squared minus x to the negative 2 in the parentheses. And then you can plug in this result of f prime to the formula of the arclength. So S equal to the integral from a to b of square root of 1 plus f prime squared. And the formula, so f prime is just 1/2 x squared minus x to the negative 2 as we did. So if you square it, you get the 1/4 from 1 square, 1/2 square. And then you square x squared minus negative 2. So you can, FOIL if you want, or use the formula as I did in here. So x squared minus x to the negative 2 squared is just x to the 4th minus 2 times x squared times x to the negative 2 plus x to the negative 4. You got two terms in the cross term, remember, when you square it. But x squared times x to the negative 2 is just the 1, all right? So that becomes 1 plus 1/4 times x4 minus 2 plus x to the negative 4. There is no square in here. I'm sorry, there's a typo in here. I don't know why I put the square in here and then in the previous step. Okay, so but then just combine like terms. So we got 1/4 x to the 4th minus half from 1/4 times 2 and plus 1/4 x to the negative 4. So and then you get 1 in the front. So just combine like terms, simplify the whole thing. And then you can combine 1 with negative half, you get positive half. So at the end, you get the square root of 1/4 x to the fourth plus 1/2 plus 1/4 to the times x to the negative 4. And then we're going to simplify this a little furthermore. All right? Okay, so that's what we got on the last page. S equal to 1/2 to 2 of square root of 1/4 x to the fourth plus 1/2 plus 1/4 x to the negative 4. Remember, in the previous problem, we need to find the arcnames from x equal to half to 2. Okay, so integration is from half to 2. It's not from 0 to 1. All right? So, and then we can take out 1/4 from inside of the radical. And then if you do that, you're going to get the x to the fourth plus 2 plus x to the negative 4. You can easily verify that. And again, you can take the root of 1/4 to get 1/2. All right, out of the radical. But then x to the fourth plus 2 and x negative to the 4 inside it can be factored as squared plus x to the negative 2 squared. If you do that, you can easily check it if you want. And then if you take the square root of this perfect square, you get just x squared plus x to the negative 2. Okay, so then you can easily integrate the two terms by using the power rule again. So we got 1/2 times x cubed over 3 plus x to the negative 1 over negative 1 from 1/2 to 2. So then, we just plug in the numbers and subtract it. But let's just rewrite the second term as negative 1 over x. Negative 1 in the denominator gives you the negative sign. X to the negative 1 gives you the x in the denominator. All right? So we got 1/2 times x cubed over 3 minus 1 over x. And then you subtract 2 for x and subtract 1/2 for x. And simplify. So you get 1/2 times x, 2 cubed over 3 minus 1/2 minus 1/2 times 1/2 cubed over 3 minus 1 over 1/2. And 2 cubed is just 8, and 1/2 cubed is just 1/8. And then you just do this simplification step by step with the fractions. So at the end, you add, subtract those fractions, combine those, you get 33 over 16. So that's the final answer. You can easily check it. So that's about the arclength. And the other thing is the area of a surface of revolution in this section. So we try to rotate a curve, a plane curve, as shown in the graph, about the x-axis in this case. So this curve is y equal to f of x. So that's the function, the graph of the function. And we want to find the surface area when you rotate this curve about the x-axis. You got the surface like this on the right side of the graph. And then we want to find the area of this surface. So again, you just cut the curve into many pieces as before, and then approximate each piece of curve by line segment shown in the graph. We call it delta Li. Okay, and then we can easily find the surface area of that piece of line segment. The band. If you rotate that line segment, the band, you get a band as shown on the right, the yellow band, and that surface area is easy to calculate. And that turns out to be 2 pi times f of xi times li for the formula of the surface area of the band. All right, and then you just do the same process as we did. Add them up and take the limit. Also, we use the same trick as before. You rewrite the second term of delta y squared as delta y over delta xi squared times delta xi squared, so that we can factor out delta xi. And then we got this limit of the sum of 2 pi f of xi times square root of 1 plus delta yi over delta xi squared times delta xi. And then when you take the limit, this sum becomes integral, and delta y over delta xi, as we did before, that's just the slope of the tangent line. Okay, so at the end we got the formula. The surface area is equal to the integral from a to b of 2 pi f of x times square root of 1 plus f prime squared. So just plug in the formula when you do the problem. You don't have to cut anything, you know. So let's do a couple examples. So example 1, find the area of the surface obtained by revolving the curve fx equal to x cubed by the x-axis from x equal to 0 to x equal to 1. So fx equal to x cubed. So you take the derivative, you get 3x squared, and then plug that into the formula. So we got s equal to 2 pi x cubed, that's the f of x, times square root of 1 plus 3x squared to the square, and that's from the f prime. So that gives us 2 pi x cubed times square root of 1 plus 9x to the fourth if you square the term inside the radical. And then again, we're going to use the substitution to integrate it. It's not hard. So let u equal to 1 plus 9x to the fourth, the part in the radical. So do the du. So you got the 36x cubed from the derivative, and then times dx. So dx will be du over 36x cubed if you divide by 36x cubed on both sides. And then find out the lower and the upper limits of integration for u. So plug in 0 for x, you get the u equal to 1 plus 9 times 0 to the fourth. You got 1. And when x equal to 1, you got 1 plus 9 times 1 to the fourth, you got 10. So now the integral of the surface area from 0 to 1, of the integral from 0 to 1 of 2 pi x cubed times square root of 1 plus 9 x to the fourth from the previous page. It's just equal to s equal to, I don't know why I wrote this s again. So we were going to replace everything to u. So the lower limits and the upper limits of integration becomes 110 as we already did. And then 2 pi x cubed, we just copied from the first step. And u is just 1 plus 9x fourth, so that's in the radical. And dx is just du over 36x cubed. So now you can cancel the x cubed in the problem and also cancel 2. And so you get power 18 times square root of u. And that's easy to integrate. Rewrite the square root of u as u to the half and then integrate. So we got 18 over 8 power 18 times the 2/3 u to the 3/2. And then you just simplify to power 27 if you multiply these two fractions and simplify, and then plug 10 and 1 for u and subtract. So we got power 27 times 10 to the 3/2 minus 1 to the 3/2. But 1 to the 3/2 is just 1. So at the end, we got power 27 times 10 to the 3/2 minus 1. So that's the answer for this problem. Let's do another easy example. This one will be a little easier. Okay. So we want to find the area of the surface obtained by revolving the curve of fx equal to 2 square root x by the x-axis from x equal to 3 to x equal to 8. So we don't have to do the graph. We have all the formulas, just plug in. So fx equal to 2 square root x, you can rewrite it as 2 to the x half, and then take the root, square, take the derivative. I got a little error here. The x should not be in the exponent or something, so that's 2 times half x to the negative half, and 2 and 2 half get 1. So the derivative is the x to the negative half. So plug that in the formula. We got 2 pi times f, which is 2 times the x to the half, square root of 1 plus f prime squared, which is x to the negative half squared. But the x to the negative half squared is just x to the negative 1. Remember, when you take the exponential, it is multiply negative half by 2, you get a negative 1 in the exponent. And then, so we write the x to the half inside the integral to square root x, okay? So we get 2 pi times 2 times square root x times 1 plus x to the negative half. And then we combine these two radicals to get x times 1 plus x to the negative 1 using the properties of radicals. And 2 pi times 2 is just 4 pi. So then you can distribute the x inside the radical to the two terms. You get x plus 1. Remember, x times x to the negative 1 is just the 1. All right. So that one is very easy to integrate, I guess. We just use the power rule. I don't know why I wrote the s again here. So what you do is just you write square root of x plus 1 as x plus 1 to the half. And so then integrate, you get the 2/3 times x plus 1 to 3 halves using the power rule. And then just plug in 8 and 3 into the problem, the result for x. So we got 8 pi over 3 if you multiply 4 pi with 2/3 times x to the x plus 1 to 3 halves, and then plug in 8 and 3. So we got 8 pi over 3 times 8 plus 1 to 3 halves minus 8 pi over 3 times 3 plus 1 to 3 halves. So 8 plus 1 is 9 and 3 plus 1 is 4. So we got 8 pi over 3 times 9 over 9 to 3 halves minus 8 pi over 3 times 4 to 3 halves. And then you can easily find the 9 to 3 halves by taking the square root of 9, you get 3, and then you take the cube of 3, you get 27. Similarly, you do 4 to 3 halves by taking the square root of 4, you get 2, and taking the root of 2, you get 8. So we get 8 pi over 3 times 27 minus 8 pi over 3 times 8. And you can factor out 8 pi over 3, and so you get 27 minus 8, which is 19. So at the end, if you multiply them out, you get 152 pi over 3. So that's the end of this. That's the final answer.